Right, thank you for having me. Really happy to be here. I'd like to present my work that I did together with my group at the University of Wolverhampton in the UK on restoration of spaces, punctuation and capitalization. I believe Hughes is on the call as well today, so he may participate later if we have any questions. The other two authors were unfortunately unable to make it today. This is the structure of the talk I'd like to give today, which corresponds to the sections that we have in the paper itself. So I'll start by just introducing what it is we set out to do, go briefly through some related work, and then introduce the models that we built, the experiments that we ran, and the results of those, and finally some conclusions. So first of all, to introduce the work. So the work is connected to the field of speech recognition in that, first of all, we recognize that speech recognition is becoming more and more widely used in recent years. And it's our understanding that many state-of-the-art ASR systems do not render punctuation or capitalization in their outputs. And obviously these are essential features of text. So we saw punctuation and capitalization restoration as very relevant and important topics. We also include space restoration in our study. This may not be required for ASR outputs, but can be useful for other applications such as parsing hashtags. So this is an example of an input into one of our models. This is an extract from a TED Talk transcript, which was one of the main data sets that we used in our study. So the input would look like this, consisting of only lowercase letters and digits. And our models attempt to restore capital letters, spaces, commas, and periods to hopefully render outputs that look something like this. There is a good amount of existing work on each of the topics that we covered, which we'll cover in the next section. But some of the limitations of those that we recognized is that, especially with regard to punctuation and capitalization restoration, most work tends to approach the problem from a token level perspective. So models are unable to restore capitalization or punctuation that occurs mid-token, such as in the capital P in iPhone or the dot in yahoo.com. And this also means that they can't be applied directly to scriptio continua languages. So those are languages without spaces like Japanese, Chinese, Thai, etc. In those cases, it's common to apply a word segmentation prior to restoring punctuation and capitalization, but of course that can lead to further inaccuracies from those segmentation models. The related work, so first of all, space restoration, word segmentation. There's a rich body of literature on this because of the need for word segmentation for those, especially Asian languages like Chinese and Japanese. We see that this has evolved as neural networks have become more and more common. And we do also see in this particular domain a sort of recognition of the advantages of character-based approaches as opposed to token-based approaches, and a lot of work trying to create hybrid models that bring together maybe dictionary-based token approaches with a character-based approach. In capitalization, punctuation restoration, similarly, we see more and more sophisticated models with neural networks, transformers, pre-trained language models, but very few studies looking at character level approaches. In this list we've got here, there's just the one study at the bottom that did approach it from a character level. In terms of our overall task, we're only aware of one other paper that has covered this. So that's bringing spaces, punctuation, and capitalization together in a single model. This was Shiva Kumar et al. In 2021. They used bigram level GRUs. They adopt a pipeline approach One of the interesting things about the paper is that they experiment with different orders of restoration, and they actually find that the best results they get for that particular model are not restoring spaces first, as we might intuitively think, but they actually restore periods first, followed by commas, spaces, and then capitalization. And this is a sample output that they include in their paper. Okay, I'd like to go briefly through the models that we used in our paper. We have started off with 5 different types of models, and some of these are only for space restoration. So that's 1 and 2. 3 and 4 are specifically focused on capitalization and punctuation, and the 5th model does everything in a single step. So that's an end-to-end model. We also looked at a combination of statistical machine learning models and deep learning models, and a combination of character and token level, as suggested by the name of the paper. First model is a naive Bayes model for space restoration only. I won't go into too much detail on how that works because it's implemented based on existing work. But we start off with our, so for training, we start with a gold standard output. We segment that into tokens. We count the tokens to get probabilities for each token. And then we use a naive Bayes-based algorithm with dynamic programming, smoothing, to get the probability of each possible candidate segmentation or candidate space positioning for the string. We showed unigrams here, but the model implemented in the paper uses both unigram and bigram probabilities. Model 2 is a bidirectional LSTM character-based model for space restoration. So here we would just assign a class to each character based on whether or not a space should follow that character. So the ones here represent a space following a character. The model architecture looks like this. So we have both the forward and backward LSTM layers that so incorporate memory about what comes after as well as what came before each character. Those outputs are then combined and passed through a sigmoid activation layer. Third was a CRF, conditional random field model. So again, this is a traditional statistical machine learning architecture. The features used for that model were things like the current word, the part of speech tag, and the word and part of speech tags for the 2 words that follow the current word. Fourth model is this is a token-based bidirectional LSTM that also incorporates a pre-trained BERT layer. The architecture looks like this. So the inputs are tokens, and before the biSTM layer, we have a pre-trained BERT layer, and finally softmax activation. So for this one, we combine capitalization and punctuation, and so we have classes such as a token that only has a comma after it, or a token that is both capitalized and has a full stop. So it's a relatively small number of classes pertaining to tokens. The final model is yet another bidirectional LSTM. This is character-based, and this is the only model that does everything end to end. So it's restoring spaces, punctuation, and capitalization in a single model. So there's a much larger number of possible classes here. I believe it was 16 classes because we have 4 types of feature. So we can see here how some of the classes that we would get for a sentence like this. So here 2 is only a space following a character. 3 represents that the character is capitalized and has a period. 4 represents that the character is capitalized and has both a period and a comma and a space following it. The architecture is very similar to that for model 2, just with a larger number of classes, and we use softmax activation here rather than sigmoid for multi-class classification. So with the five basic models, we generated pipelines. So this gives us again a total of 5 pipelines that are capable of restoring spaces, capitalization, and punctuation. The experiments, so we mentioned various languages in the title of the paper. The languages that we looked at are English, Japanese, and Gujarati. This gave us a broad variety of languages from different language families. We also have a unspaced scriptio continua language in there and a low resource language. Our main data set for English was a data set of transcripts of TED Talks. We also used a second data set, which is the Brown corpus, for comparison with previous work, and compiled our own corpora for Japanese being taken from a popular Q&A website, and for Gujarati we used news data. So these are the results. First of all, so in the paper we have a breakdown of precision and recall for each of the different features, for each of the different models on each of the different data sets. Here we just summarized the overall F-score that combines all features. And we find that the pipeline combining the best from, so naive Bayes, BISTM, char space had very similar results, both very high accuracy for spaces. The pipeline taking the best of those 2 models and then putting those outputs into the BILSTM model with pre-trained BERT layer gave us the best results. However, we also see good results. So F-scores of 0.9 on the TED Talks dataset with the end-to-end model. Also for Gujarati. For Japanese, we see a lower score, although we believe this to be largely because spaces are not among the features assessed. So we actually believe this to be a relatively good score for Japanese language. And then we also calculated word error rates for each of the models, which tell a similar story. This is an example of the output from the BISTM model with BERT, which does show, really how good the outputs are, how capable this pipeline is of restoring all those features. So there's only one part where the output differs from the reference output, but this is actually not incorrect either. It would not be incorrect English grammar to combine those sentences and use a comma. For space restoration, we saw very high performance from both the traditional naive Bayes model and the BILSTM based model. The BILSTM character-based model did seem to cope better with unseen vocabulary, which could be an advantage. Sometimes it produces outputs that are not. So we have an individual S in the example at the bottom here. So incorrect spelling, but at least this is easier to detect than an incorrect segmentation. The highest performing model for capitalization and punctuation restoration was BERT BILSTM, but we did see that the character-based end-to-end model was successful in restoring that mid-token punctuation and capitalization that we talked about at the start. So for example, BC with a dot between the B and the C, and the capital D at the end of PhD. For the other languages, we, apart from the observation about Japanese that I made before, we saw a very high overall score for Gujarati, which we believe may be due to having used more regular data, like being news data. And we also discovered during our experiments that we had to take into consideration grapheme clusters in Gujarati because byte level models did not take into account the typographical characteristics of the language. So we adapted the end-to-end model to be able to handle Gujarati. For future work, we'd like to, there are some improvements that could be made to the BILSTM model. So we'd like to see just how good performance we can get from that. We're also very interested in using character-based so pre-trained character-based language models, as all of our results suggest that these could be very advantageous for the task under consideration. Finally, just want to point out, so in the paper, we have a link to a portal page, which links to a total of 6 different GitHub repositories with all of the code that we used in the paper and comprehensive documentation and Google Colab notebooks that enable people to see the code being used. Thank you very much.